Hello, this presentation is about significant figures, measurements, and converting units. We're going to add one more thing to that list. We're first going to talk about measurements and what that means. We're going to talk about how accurate a measurement is by the number of significant figures it has. There's sometimes that you're going to have to convert your significant figure values to scientific notation, and we'll go over that. And lastly, we're going to learn about something called unit analysis, which is a method of converting units. Now, this may sound really scary, but it's not at all. You're going to see how easy it is. All right, let's start out by talking about measuring in the scientific laboratory. Scientists use a system of units called the SI system or International System, and it's also called the metric system. It's based on the unit 10, so it's very easy to use, whereas the US system has all kinds of different conversions, like 4 cups equals a quart, 12 inches equals a foot, that kind of thing. But the metric system is much easier because everything is in units of 10. And here's a list of the basic quantities for various things. We're going to pretty much be using mass, length, and volume. Those are the 3 things we use most in chemistry. So we'll be talking a little bit about those. What you do with the metric system is you use that base unit, and then you put a prefix on it to make it bigger or smaller. For example, let's say that I want to use the metric unit of liters, and I wanted to talk about something that is 1,000th of a liter. I would put this prefix on it to call it a milliliter. Most of you have probably heard of a milliliter. If I wanted to make something bigger, like let's say I had the kiloliter, that would be 1,000 liters. That would be where you're measuring maybe the number of liters in a milk truck or something like that. All right, but you can put these prefixes on any of the basic units to make them larger or smaller. Okay, one thing I want to mention real quick is why we use the liter as the system or our basic unit for volume in chemistry. Cubic meters are very large, and in the chemistry lab, we're going to basically be using tiny units normally. So we're going to cut that down to what we call a cubic centimeter, sometimes called a cc. If you guys work in the medical field, you'll recognize that term. A cc or a cubic centimeter is also equal to 1 milliliter. So a milliliter is the 1,000th of a liter. So we use the liter as our basic unit for volume. Now, I want to talk about significant figures because that's going to tell us how accurate a measurement is. Accuracy is the closeness of your measurement to the actual value. Don't confuse that with precision. Precision means that you keep measuring some thing, like a piece of wood, the length of a piece of wood or something, and you keep getting the same value over and over or something really close to it. That's not always accurate, because if your measuring device is off, you could measure something several times to get the same value, but since your measuring device is off, it's not going to be an accurate measurement. But we're concerned mostly with accuracy. So we want to have our value be the real value. So when you measure something, you are going to use a particular measuring device, and that device is going to limit the accuracy of your measurement. I'm going to show you why in just a second. The last value of your significant figures is going to be a guessed value. Let me show you what I mean by that. And also, as I go through this, instead of having to write out significant figures every time, that's a pretty big word, I'm going to abbreviate it as SF. All right, let's look at this ruler. This is a metric ruler, so these things are what we call centimeters on this, and I'm going to measure a piece of wood. All right, now notice there are just the only increments on this particular measuring device are 1, 2, 3, 4, 5 centimeters. So what I'm going to do is I'm going to say, okay, I know my piece of wood is 3 centimeters. Now I've got to guess the next value because I don't know for sure what it is. I'm going to guess it's a 2. So what I would say is, okay, my piece of wood is 3.2 centimeters, where 2 is the guessed value. That means I have two significant figures in my measured value. Now let's do another one where the accuracy of our measuring device is a little better on this one, because you can see that I've got now 10 little increments between my centimeters. Those are called millimeters. So what I can do now is I can say, okay, this piece of wood is 3.2 centimeters, but it's a little bit more than that. I've got to kind of look at my wood and kind of estimate where the end value is there, but I'm going to say it's 3.24 centimeters. Again, the 4 is my guessed value. Okay, so let's look at this again now. 3.2 centimeters for my first one had two significant figures. 2 is the guess value. My second measurement was, we had 3.24 centimeters, and we had 3 significant figures where 4 is the guessed value. Hopefully you all kind of got the feel for what this means now. Now, this is kind of weird. I'm transitioning into scientific notation real quick, and then we're going to go back to significant figures in a little while. You'll see why I'm doing this in a moment. Scientific notation is a method of writing numbers where you write the first value as a number between 1 and 10, not including 10, times 10 to some power. And we'll go over some examples of this in a moment. Scientists use this method for 2 reasons. Number one is our purpose. It's a way of showing the number of significant figures. Second reason is sometimes if you have really large or small values, this makes them easier to deal with. All right, small numbers in what I'm talking about here are going to be values where the decimal point is to the left of the first digit, something like 0.011. Large numbers are those where the decimal point is to the right of the first digit, something like 1,100. All right, let's talk about how to change numbers to scientific notation. First of all, you're going to move the decimal point to the right of the first non-zero digit, counting the number of places you moved it. If it's a small number, the exponent is negative, and you put that number of places you moved it as a negative number. If it's a large number, the exponent is positive, and again, you're going to put the number of places you moved the decimal point as the exponent. Let me show you some examples. All right, let's say we have this number, 89,800,000,000. This is a big number, obviously. So what we're going to do is we're going to say, okay, we're going to say that this is the number, this number of significant figures end right here at this 8. And so I'm going to say there's 3 significant figures in this value. But I had to put the zeros on there to tell me how big the number was. But I want to show it as 3 significant figures. So what I'm going to do is I'm going to change this to scientific notation by moving a decimal point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places to the left. Okay? So my exponent is going to be 10. So I can rewrite my number down here as 8.98 times 10 to the 10th power. And that shows my 3 significant figures. Now, here's a small number, and I'm going to again do the same thing, but remember, with a small number, your exponent is going to be a negative number. All right, and I want to move my decimal point to the right of the first digit again. My arrow is a little off there, but it should be right here, in between those. All right, so what we're going to do is count the number of places we move a decimal point. Well, I'm moving it 3 places, right? So my number is going to be 1.2 times 10 to the negative 3 power. Notice when I do this, it's immediately obvious that I have 2 significant figures in my answer. Okay, let's see if we... All right, one other thing I want to mention is if you have a number that you need to write in scientific notation, but it's already written as the decimal point is to the right of the first digit, you can write it as that number times 10 to the 0th power. Why is that? Well, to any number to the 0th power is 1, always. So if you write it this way, 8.67 times 10 to the 0th power, you're actually saying 8.67 times 1. Or 8.67. I don't know why that 8 is there, so ignore it. All right, to change from scientific notation to normal notation, you're going to do the reverse. In other words, I'm going to look at my power, and I'm going to move a decimal point that many places. And in the case of a big number, remember the decimal point is positive. I'm going to move a decimal point right. So you're going to have to add some zeros to this to do that. So I'm adding a bunch of zeros, and I'm going to move my decimal point 6 places to the right. So I end up with this number. Now notice that it's not obvious how many significant figures I have here if I write it in normal notation, but I end up with 9,670,000. Let's do the opposite now. Let's change a little number to normal notation. Again, you're going to move the decimal point this time to the left because we have a negative exponent. And if you do that, you end up with 0.0000412. And it's immediately obvious how many significant figures there are here, but you don't know that yet because I haven't gone over that part. But we're going to do that now. All right, so with significant figures, zeros are a really important thing. Number one, do not count zeros to the left of the first number. Remember, I just mentioned that in that last slide, that you would recognize the number of significant figures in a small number because you never count the zeros to the left of the first digit. So this number would have 3 significant figures. Okay? Do count zeros in the middle of a value. So if you look at the second one here, I'm going to start counting at my 3, and I go 1, 2, 3, 4. It has 4 significant figures. All right, do count zeros at the end of a value. So in this case, I'm going to start at my 9, count over the number of places, and there's 4 significant figures. Now, if I couldn't show that, like in number 4 here, if I could not show that there's 3 significant figures with the number the way it's written, you must rewrite it in scientific notation. So, for example, let's say that we have 234000. And we want to show that it only has 3 significant figures. Well, what I got to do is rewrite it in scientific notation. Notice I would move my decimal point 5 places to the right. So my 10 is going to be raised to the 5th power. And I just write 2.34. That immediately shows me that there's 3 significant figures there. Okay, a couple of rules about multiplying and dividing significant figures. For multiplying and dividing, what you do is you count up the number of significant figures in each of the values. Do not include exact numbers. Exact numbers are things like there's 1 foot in 12 inches. Those are considered exact values because they were created to be that. So something like that, don't include those numbers. But include only measured numbers in this. So what you would do is you count up the number of significant figures in each, and you're going to write the answer to the smallest number. So go ahead and multiply and divide your number and round to the smallest number of significant figures. Let's do an example. All right, here's a formula. We want to find the area of a triangle. Well, the formula for that is 1/2 the base times the height. Where the base is, B is the base, H is the height. All right, so let's say that our base is 6.732 inches. That's 4 significant figures. And our height is 5.43 inches. There's only 3 significant figures in that one. The 1/2 is considered an exact number. It's not measured. So we go ahead and multiply and divide everything, and we end up with 18.27738. Now, I want to show that there's 3 significant figures because that's the smallest number of significant figures in my string. So I would just round off the 18.27 to 18.3. And that shows me that I have 3 significant figures in my answer. And notice the units here would be inches squared because we're doing an area. Okay, adding and subtracting significant figures. Line the numbers up vertically at the decimal point. Determine which one ends furthest to the left. Add and subtract your numbers and round to that place. Sometimes you've got to rewrite in scientific notation to do this. Let's do an easy one first. All right, let's say we have 3 different guys measuring some pieces of wood with different measuring devices that have various degrees of accuracy. The first one only is accurate to the 10th place, so it's 1.2 feet. The second one is a little bit more accurate, so 5.43 feet. And the third one is much more accurate, is 6.193 feet. So we're going to add those up now. And we're going to round off to the 10th place because that's the one that ends the furthest to the left. So we end up with 12.823, and we got to round it at the 8. So my total length of those pieces of wood is 12.8 feet. Now let's do one that's a little bit trickier. Let's say that I have the following 3 measured values. 1.23 times 10 to the 4th kilogram. That shows that there's 3 significant figures in my answer, right? And the second one is 234.1 kilograms. And then I've got 61,089 kilograms. All right, I'm going to go ahead and change my scientific notation to regular notation, but I'm going to make a note that the significant figures end at the 3 here. Now let's go ahead and line our values up and add them all together. So I'm lining them up, I'm adding them all up, and I end up with 73,623.1. Now remember that my significant figures had to end here at this 3, so let's go down and find that. Well, that would be ending at the 6 here. All right? So rewrite that as 7.3600. Remember now, we need to write that in scientific notation to show that there's only 3 significant figures. So we would write it as 7.36 times 10 to the 4th kilograms. All right, so that's how you add and subtract these. Now, let's go over something called unit analysis. Sometimes it's called factor label or dimensional analysis. And I'm going to go ahead and just kind of explain what this means. We've learned about fractions in previous courses, I'm sure, and you guys have all probably recognized the fact that if you have numbers like, for example, 20 over 75, you can write those out in prime form, and any numbers that occur on the top and the bottom can't be canceled. So I could cancel out the 5 here and the 5 here, and I would go ahead and multiply those things back together and get 4/15. That's not the point of this, so if you're not following, it really doesn't matter. The point of this is that I could do the same thing with units. Let's say that I have a 5 feet times 12 inches over 1 foot. All right, I could rewrite the 5 foot as 5 foot over 1. And notice that I've got a foot on the bottom and a foot on the top. So I can cancel those out, just like I would numbers. And so if I do that, I have 5 times 12 on the top, inches, the unit left is inches over 1, or 60 inches. That's the whole idea of this technique. And here are some other conversion factors. There's a bunch of them that you probably recognize here, like 5,280 feet equals a mile, 3 feet equals a yard, 4 cups equals a quart, etc. There's a zillion of these. You can get on Google and find pretty much conversion factors between any kind of units that you want. Here's some metric unit conversion factors just for your information. If you ever want to find this and you want to find this slide, just go ahead and run the video again and pause it at this point. But let's explain how this works now. Let's say that I have 2 measuring devices here. One of them is a foot long, and that's all it's got on it, nothing else. The other one has it divided up into 12 inches. Now these 2 measuring devices are the same, or these 2 things are exactly the same thing, aren't they? In other words, 1 foot equals 12 inches. They're the same thing. So if I write those as fractions, if I write 12 inches over 1 foot or 1 foot over 12 inches, they both equal 1 because they are the same thing, and the same thing over the same thing always equals 1. If I have 5 over 5, that's 1, correct? If I have 80 over 80, that's 1. So since these are the same thing, these conversion factors actually equal 1. So what I can say is I can write my conversion factors as the 12 inches over 1 foot or 1 foot over 12 inches. But it's the same thing as multiplying something by 1 because the same thing over the same thing. So what am I going to do here? All right. The steps for using these conversion factors and doing converting factors using unit analysis is the following. Look at the unit you're starting with. Determine what unit you want to end up with. Find the conversion factors that you need to get from where you are to where you want to be and arrange them so that the units cancel properly. Cancel all the units, multiply and divide the numbers, and then if you were doing this for a project or something, you would want to write that out in words at the end. So let's kind of look at a problem, and we'll go through an easy one first. Let's say that we have a plank that is 48 inches long and we want to know how many feet it is. Well, this is pretty simple. You could do this in your head because you know there's 12 inches in a foot. But I'm going to show you how to do it using this method. All right, so I know my conversion factor. I'm starting with inches. I want to get to feet. That's the first couple of steps. What conversion factor do I need? Well, I need 12 inches equals 1 foot. And I can write that one of two ways, either 12 inches over 1 foot or 1 foot over 12 inches. I want to write it so that the inches will cancel. So I'm going to write it as 1 foot over 12 inches because look what happens here. If I write 48 times inches times 1 foot over 12 feet, or excuse me, 12 feet, 1 foot over 12 inches, the inches cancel. And I am left with 48 feet divided by 12 or 4 feet. Now, notice that this is a measured value, this 48, so that's got two significant figures. So instead of just writing the answer as 4 feet, I want to write it with two significant figures, so I would write it as 4.0 feet with two significant figures. Let's do another. Let's say I want to convert 2.00 miles to inches. Well, this again is a measured value, so I'm going to write down, I'm going to say, okay, there's 2.00 has three significant figures. Put a pin in that to remember it. I'm starting with miles, I want to end up with inches. All right, from my list of conversion factors I gave you, I need two of them. 1 mile equals 5,280 feet, and 1 foot equals 12 inches. Let's write this out now. 2.00 miles times, let's write a conversion factor so the miles cancel. So I would write the feet on top, so 5,280 feet over 1 mile, the miles cancel. Next I want to convert feet to inches, so I would write as 12 inches over 1 foot, the feet cancel. And so I'm left with 2 times 5,280 times 12 inches. All right, so multiply that stuff all together, and you get 1,206,720 inches. I need to write this with three significant figures because I started with three measured significant figures. So I would write this as, I rounded off to this spot right here, so it'd be 1,237,000. Now I need to write that in scientific notation to show that it only has three significant figures. So I would convert it as 1.27 times 10 to the 5th inches in 2.00 miles. Now notice so far I've been doing this with the U.S. system of units because you have to use this method with the U.S. system of units. There's no easy way to do conversions in the U.S. system. With the metric system, you can convert units by just moving the decimal point. That's a topic for a whole new PowerPoint. I'm not going to cover that here, but I do want to show you that you can use this method for converting metric units if you want to. There's a much easier method that maybe I'll give you guys at another time. All right, let's say I want to convert 2.5 kilometers to centimeters. All right, what am I starting with? I'm starting with kilometers. I'm ending with centimeters. So I want to write down my two conversion factors I need to convert here. 1,000 meters equals 1 kilometer, and 1,000 centimeters equals 1 meter. All right, so let's arrange. 2.5 kilometers, I want to first convert from kilometers to meters, so I'm going to write my conversion factor so kilometers are on the bottom. So it's 1,000 over meters over kilometers. Kilometers cancel. Next, I want to write my centimeters on top and my meters on the bottom so that the meters cancel. So I'd write 1,000 centimeters over 1 meter. Notice the only unit I'm left with is centimeters, so I'm going to go ahead and multiply 2.5 by 1,000 by 100, and you get 250,000 centimeters. I started with only two significant figures, so I've got to change this to scientific notation to show that. Moving a decimal place 5 places to the right, so I would rewrite that as 2.5 times 10 to the 5th centimeters, and there are that many centimeters in 2.5 kilometers. That's it. I hope this was helpful. Let's see here. I want to shut